Kia ora, Year 12. This video is going to look at parametric differentiation and parametric equations. So this topic is covered both in the Pure 3 exam for A-level and also in Level 3 calculus in the differentiation paper. The big idea here is that we can have two variables that are defined indirectly through a third variable. And in just a minute, you're going to go and have a play around with Geogebra to see how that works. Okay, so instead of having just a relationship where y is equal to blah, 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 x. So for example, y equals 2x minus 1. Right, when we first learnt about functions way back in probably year 8 or year 9, we had this idea that we took an x value and we put it into some kind of function machine, right? And so we took that number and we times it by 2 and we took away 1 and out popped y. So the idea here is that there could be a third parameter, which is often going to be t or theta, and x depends on that parameter and so does y. For example, this one here. X is cos theta and y is sine theta. So you can see that you've got theta affecting x and theta affecting y. And that means that indirectly there's going to be a link between these two variables. Now, sometimes you can rewrite the equations so that you can get them in terms of each other with no third variable. I'm not going to go over that in this video, but we'll be looking at that as we work through exercise 4e. So there's a second example there where the parameter is t, right? So x is equal to 5 times t and y is equal to 2t squared plus 1. If you wanted to trace out how to draw that graph, what you could do is just pick different values for t and then you'd work out your value for x and your value for y. And you'd get your Cartesian coordinates for the things there, right? For example, if t is 0, x is going to be, using this one here, 5 times 0 is 0, 2 times 0 squared plus 1 is 1, right? When t is 1, x is going to be 5, and y is going to be, let's see if I can do it, 2 plus 1 is 3. T is 2, we get x is equal to 10, and y is equal to 2 times 4 plus 1. So we've got a quadratic thing going on there. And we could graph it. Right. What I'm going to do now, though, is get you just to work with this GeoGebra link. Now, I didn't write this. This is a really, really cool applet that we're going to be using today. Right. But just before we do that, I want to tell you what we are and aren't going to do in today's lesson. So we're going to look at what the curves look like. I'm going to give you a bunch of different equations to put into that applet, and I want you to have a play around. These curves are pretty fun, and so if you want to just play around and find some more funky looking shapes, then go for it. But remember, we've got to get through quite a few examples as well. Then the main thing that I'm going to do in this video is discuss how can we find dy by dx, right? Things that are coming up in future videos, because I'm going to be away all week, are how we get rid of the parameter, how we find the equation of the tangent or the normal at a point, and how to find stationary points. The main exercise for this that we'll be doing is exercise 4e in the textbook. I've put it into the tracker sheet and full worked solutions are up on Google Classroom and they're also linked in the tracker sheet. Okay. So what I want you to do now is to go to this GeoGebra link. I'll be posting that link directly onto Google Classroom later on today, or you can just type it out from there. And what you'll see is an applet where you can type in pairs of equations for x and y. I'm going to try and go over there now and see if this works. Right, so you should have a window that looks like this one. Let me just see if I can move. Yeah, there we are. So your window looks like this. Type in those different equations for x and y, and if you click on the animate button, it will do cool things for you. The value of t is where you can change the parameter, so you can play around with that as well. Let's not waste time on that now. Okay, so going back into OneNote, these are the pairs that I want you to try out. And you should be able to generate some of the following pictures. So there's one. See if you can match up those equations with these pictures. I think I've missed some of the equations out, but what you're going to want to do is to play around with the coefficients here. Right, so this is just one pattern type, but these are some trig parametric equations. So you can muck around with the 2, the 6, the 4, and so on, and just see what you can draw. So these are some of the shapes. And you'll notice from here, and the reason why I'm doing this is to show you that we haven't got a function, right? We've got a relationship between x and y. So what that means is that every point on this curve is associated with a particular value of theta. right? And we can see that at a lot of places on this curve, we can draw a tangent, right? So the obvious question is, well, how do we get the gradient function when we're not working with, you know, an ordinary old y equals blah, blah thing? So the goal by the end of this exercise is going to be that we can take a set of parametric equations like these ones here, and we can differentiate them, and somehow we want to be able to find dy by dx. And then we want to be able to say, well, look at this point here, point P, how can I get the equation of the tangent? Or, you know, the obvious next question, especially if you're a Cambridge exam writer, is how can I get the equation of the normal? And that's going to use all of our earlier coordinate geometry stuff. Then the other thing we're going to want to do is to say, well, where are the stationary points? Right? So you can see on here, you can see a stationary point up here, for example. So how can we figure out where it is? Well, to do that, we're going to have to solve for where the gradient function is 0 and then work backwards to find the parameter value of theta or t. But that's not going to be in this video. Okay, so let's just keep on looking at these curves. I told you they were pretty cool. There's another one. Here's another one. Looks kind of like a scoopy flower. And then this one here, I think, is my favorite from the ones I've done today. So see if you can draw those graphs. And what I'm going to do now is go on and look at how we can use the chain rule to find the derivative dy by dx. Okay, so we don't need to have y equals blah, blah, blah to have a link between the two things. And when we learned implicit differentiation at the end of last term, we used the chain rule. And we're going to use it here as well. So we've got x is equal to some function of t. And we've got y is equal to some other function of t. So we can find the impact of a change in t, a tiny change in t, on x, and that's just dx by dt. We can do the same thing with y. We can find the impact of a tiny change in t on y. And so now we can use the chain rule to put those two things together. So dy by dx is equal to dy by dt times dt by dx. This one here we've already got. Now dt by dx we haven't got yet. We want to figure out per tiny change in x what happens to t. But that's the same as saying this, right? So dt by dx is 1 over dx by dt. We really can treat these things just like ordinary old fractions. Okay, I think we'll talk about this more when I'm back in class, because I think that this is often kind of feels like we're cheating, and I want to show you why that's not cheating, but I've already used up 8 minutes, so I'm not going to do that today. But in general, this is what we're going to use over and over again, because what we can do here is we can say that dy by dx is equal to dy by dt divided by dx by dt. Sometimes you'll see that written as y dash over x dash. I like writing it out fully with Leibniz notation, because when we come to do the second derivative, we're going to use some of these ideas, okay, more than if we just have y dash over x dash. Because central to this whole idea is that there's a little change in t happening, which is driving the change in y and driving the change in x. Okay, 3 examples for us to try now. Skills that you're going to need to do these, quite a lot of the earlier level 3 achieve level differentiation. So you need to be really confident with the chain rule. You have to be able to differentiate trig functions, and you're going to need the product rule and sometimes the quotient rule, but not for these ones. So let's have a look at these, and these are actually pretty straightforward once we've got the chain rule stuff going. So question 1, we get dx by dt is equal to 2 times t plus 1. dy by dt is equal to 2 times t minus 1. If that's not feeling easy at this point, you need to go back and do some work on your chain rule. So dy by dx is dy by dt times dt by dx, which is equal to y dash over x dash. So we get straight to 2 times t minus 1 over 2 times t plus 1. Simplifying that gives me t minus 1 over t plus 1. Okay, and that's my final answer. So the derivative, the gradient on my graph, is going to depend on the parameter value of t. Question 2 is a little bit harder. It's got the product rule and it's got some trig derivatives in it. Okay, so pause the video and try that one now. And I'll do it here. So x is equal to theta sine theta plus cos theta, and y is equal to theta cos theta minus sine theta. You might want to go back over to Geogebra and just have a look at what that curve looks like. So dx by dt is going to require the chain rule, and not the chain rule, it's going to require the product rule for this bit here. Right? I've got theta times a function of theta. So dx by dt will be theta times cos of theta plus 1 times sine theta minus sine theta, right? Because when I differentiate cosine of theta, I get minus sine theta. Cleaning that up gives me theta times cos of theta, which is quite nice, right? dy by dt is equal to theta times negative sine theta, right? So this is u and this is v. So I've got u v dash plus v u dash. Most of you by now should be past having to write those out explicitly though. Okay, so theta times negative sine theta plus cos of theta times 1, differentiating that, minus cos of theta. Cleaning that up gives me negative theta sine theta. So dy by dx is equal to y dash over x dash, which is negative theta sine theta over theta cos theta, which is negative tan theta. Now that one comes up quite late in question 1 of 4E. And then the last one that I'm going to do is actually one that's used in the textbook but much further down with a whole bunch of other skills. So all I'm going to do here is the easy bit, which is finding dy by dx. dx by dt, very easy one here. dx by dt is negative 2t and dy by dt is equal to 2. That gives me dy by dx is equal to y dash over x dash, which is 2 over negative 2t, or negative 1 over t. So there you go, that's all for now. I will pop into the tracker sheet which questions I want you to have a go at. But when you get into exercise 4E, you'll see that by the time you get down to question 2, you're going to be finding the equation of the tangent to the curve and the equation of the normal. So we have to be substituting in particular values of theta or t. I think you're going to find that reasonably intuitive, so you can probably go a fair way through that exercise before you come to a stop. Thanks for watching, and if you need to email me, there'll be a bit of a delay this week, but you feel free to send me through questions and I'll see how I'm getting on.